All right, we're going to do integration by substitution. So this is like undoing the chain rule, basically, right? So this is where we need to identify, I guess, a little bit of patterns in our integral. So what we want to see, if we have a lot going on in an integral, we want to see a function and its derivative in the integral. Because then we can do what's called substitution and make the integral easier to solve and then go from there. So let's use a u substitution. So usually what I like to pick, if I don't immediately already see, hey, here's a function and its derivative, is I like to work with like groupings first, or maybe exponents. If we're in fractions, sometimes the denominator is something good to work with. So with this first one, I want to work with the grouping. So I'm going to do a u substitution. So I'm going to change the variable, and I'm going to say u. And I want u to be the entire expression x squared plus 1. And then remember, I wanted to see the derivative in the function. So I'm going to do it for this first one, and then I'm going to kind of like skip a step everywhere else. So if I do a derivative with respect to x, right, u is going to be du dx, and then I'll have 2x, right? I want the du to be by itself because I want the dx also to be by itself. So it's like I can multiply both sides, and I'll make that du equals 2x dx. And so for every example going forward, I'm just going to skip straight to this because I know that my dx is going to be on the right side in the end eventually anyway. So might as well just go ahead and throw it that way. And then now I see, right, I see my function here. It'll let me highlight. What the heck? I want to, because I think, I don't know. Okay. I don't know why it won't let me highlight where I want to highlight. But I see I have a u, so I'm going to write my integral in terms of u. So instead of x squared plus 1 squared, I'm going to put u squared. And then I have 2x dx, 2x dx, and I'm going to substitute that with du. And now this is an easier integral to do, and we're just doing it in terms of u. So the rules still apply. I can do power rule, add 1 to the power, divide by the new power, and then still have that plus c, right? And then I'm just going to resubstitute in the original variable. So instead of u cubed, we're going to make that x squared plus 1 cubed over 3 plus c. You can always double check yourself by doing the derivative, and you'll see you'll get back out the integral. So let's do another one. So I don't have any groupings, so I like to try the exponent. So I'm going to let u be negative x cubed. If I do a derivative, so du is negative 3x squared dx. Now it's close to what I have, right? I have an x squared dx. So what I have here is a little bit of an issue. I have negative 3 times all that. So what I can do is I can just divide both sides by negative 3, right? And then I'll have negative 1/3 du is x squared dx. And I can do that substitution. So if I rewrite this in terms of u, I have e to the u, and then times negative 1/3 du. And now what I do normally is if I'm dividing by something here, it's a constant. So I can automatically pull it outside of the integral. All right, I don't have to keep it in like this. So anything going forward, I will just automatically pull it out in front of the integral. So it's a negative 1/3, and then integral of e to the u du. And that integral is just e to the u, and then plus c. But then I want to substitute back in the original variables. So 1/3 e to the negative x cubed plus c. All right. Let's do another one here. Now I wouldn't necessarily, well, I guess you could call it a grouping. The radical, I also would try what's under the radical as my u first. Let's see if the derivative is there. So u is 4x squared plus 1. So du is going to be 8x dx. And I do see that, 8x dx. So I can rewrite my integral in terms of u. So that's going to be u to the 1/2 du. And then the integral, let's see, u to the 3/2 and then times 2/3 plus c. And then just back into the original variables. So 4x squared plus 1 to the 3/2. And then plus c. All right, I have another grouping here. So let's try that. U is x squared plus 2. So du is 2x dx. And then I have x dx, so I want to divide both sides by 2. So 1/2 times the integral of u cubed du. And then add 1 to the power, divide by the new power, and then plus c. And then I'll simplify as I go here, right? 1/2 times 1/4 is actually 1/8. And then instead of u to the 4th, we're going to do x squared plus 2 to the 4th and plus c. I have a grouping and it's in the denominator. So let's try u to be 4x squared plus 3. So the du is going to be, let's see, 8x dx. I just want x dx. I'm going to divide both sides by 8. So 1/8, and then the integral. And I'm going to do u to the -6 du. So I've got 1/8 times, add 1 to the power, divide by the new power, and then plus c. And then put back in the original variables. So I'm going to make that a -40. And then, we can go ahead and make all of this in positive exponents. So 4x squared plus 3 to the 5th in that denominator. Okay. All right. Let's do the grouping here. We got 7 minus 2x cubed. So du is going to be what? -6x squared dx. I just have x squared dx, so I need to divide both sides by -6. So -1/6, and that becomes u to the 4/3, because I have that exponent of 4 here, du. And then I can add 1 to the power, so 7/3, and then multiply by that reciprocal, and then plus c. Can do a little bit of simplifying here. 3/6 is really 1/2. And then let's put it in the original variables. So we have 7 minus 2x cubed to the 7/3, and then a negative, and then 14 in the denominator, and then plus c. All right, a few more here. Maybe we want to do long division or synthetic division to try and divide things out first. Might make things a little easier because I don't see a nice u sub to do here just yet. So let's do synthetic division and see what we get, because this is a linear term down here, so I can use that synthetic division. So I use the 0 over here in my little box, and then I need the coefficients in each place value is what I call it. So x cubed, x squared, x, and the constant. That first term always gets brought down, and then we'll multiply, and then we add straight down. So -1 times 1 is -1, and then we add. We multiply again. -1 times 2 is -2, and then we add. -1 times -3 is 3, and then we add. And then this right here is a remainder. We have a remainder of 0, which means that factor of x plus 1 is, there's a hole in the graph there. So if I go to factor that, Numerator, I could have canceled a factor out. So these become my new coefficients. If I've divided out a linear term, I go down a degree. So x squared plus 2x minus 3, and that's what we will integrate here. Right? So x cubed over 3 plus 2x squared over 2 minus 3x plus c. And then we'll just simplify. So x cubed over 3 plus x squared minus 3x plus c. I can also write that as 1/3 x cubed. It's the same thing. But I don't think if I factored that numerator that a term would cancel out. So let's do long division. So I have x squared plus 0x minus 4 divided by x squared plus 1. So x squared times what number is going to give me x squared, and that is 1. So then I distribute. So that's x squared and then 1. But this time in long division, we actually subtract the terms over. So it cancels out, and then I'm left with -5. And nothing times x squared is going to give me -5, so I am done. So then what I have left now to integrate is 1 minus 5 over, that's our remainder, right? Our x squared plus 1 dx. And then we would integrate this, and I should have looked ahead because this right here is an inverse trig, and with this class we don't do trig stuff. So let's just leave this as is and just know we could divide and make the integral simpler. We, for our sake, can integrate the 1, but in this course we don't do trig stuff, and this is an inverse trig right here. So there's nothing else we could do with that at the level we are at here. All right, so that is, I believe, yep, all for substitution. If you have any questions, let me know.